Okay, welcome to the first official episode of Curiosity Council Sundays. So, this idea came from a creator here on YouTube. I will tag her if I end up posting this, which we'll see. She liked to talk about something she found interesting for the week and then whatever topic in literature. And one thing about me and my friends, especially my friend Danny, who I'm forcing to do this with me, we like to talk about random things. And so I figured let's force us every other week to switch off topics and pick whatever random thing sparked our interest for that time. And today we're going to talk about black holes. But before we do so, I will talk about what I found interesting this week or what I learned this week, whatever. And what I learned about myself this week, which was very interesting, is that I love podcasts. And not just podcasts, but podcasts during certain tasks like driving, grocery shopping, thrifting, any task where I would typically call someone, I would call my mom or a friend and just yap to kind of avoid some of my negative thought processes. But what was really cool about podcasts is that it filled that same void, but also allowed me to continuously keep thinking, right? I kept thinking about new topics, new ideas. So I utilized the good part of my brain, the good thinking side, and still could ignore the bad stuff, or at least shovel that to the side for right now, so that didn't consume my everyday thoughts. And yeah, that was a really new and exciting and impactful uh, moment for me this week. So that's a win. Okay, now we're going to get on the topic. So this topic came up when I was doom scrolling on TikTok, as one does. And I saw this guy talking about black holes, but from Interstellar. So in the movie, he enters a black hole, he lands on this water planet, and it's very bright and sunny, or just bright, not sunny. And the guy was saying, it would be bright. However, that would be due to radiation, and all technology and yourself would die pretty much instantaneously. And I found that so interesting. And I was like, wait a second, how do black holes even work? It's so, this is where we spiraled. Okay. So I spent the last 2 weeks listening and learning from podcasts and YouTube videos, and even some uh, slides and whatnot from different sources, and I'll tag as much as possible below. I only have the tiniest bit of understanding. So at some point, I will come back to this and go over maybe another topic inside of this, right? So, first step, let's talk about the history of relativity. So, back in 1632, Galileo says, I'm captain of a ship. And if we are traveling at a constant rate of speed and we are on a perfectly still ocean, the workers below will not know if the boat is moving. And Newton took that and expanded that in 1687. And he proposed that motion is always relative to something else. His relativity worked perfectly for everyday speeds and led to the laws of motion and universal gravitation, but it assumed that space and time were fixed and separate. Now, Einstein, 2 centuries later, expanded this in 1905 through 1915. In 1905, he introduced special relativity, showing that space and time are linked, forming spacetime. And that laws of physics are the same for everyone moving at constant speeds. So think of free fall, or think of we are both in the International Space Station. We are both experiencing the uh, same gravity. I don't know how to explain that. We'll come back to that at some point. So in 1915, his general relativity then extended this to include acceleration and gravity. To do so, they used the equivalence principle. Now, this is the idea that gravity and acceleration are locally indistinguishable. They're essentially the same, right? This is the key. So imagine, space-time is a silicon mat, and we have a bowling ball, and we also have a tiny marble. This bowling ball is going to leave quite a big indentation on this mat. And if we were to roll this marble toward in the general direction of this bowling ball, it is going to curve towards this bowling ball. Now, it's not because the bowling ball is pulling this marble, it's because they follow the curved paths of the surface itself. So the mass affects the curved surface, which then affects the path. So, in short, general relativity replaced Newton's force of gravity with the geometry of spacetime. So, mass tells space how to curve, and space tells mass how to move. But this was over 100 years ago that this idea of general relativity was developed. Now, I don't know if you remember, but a while ago, people were dogging on Newton on TikTok, or maybe it was Instagram, where they were like, Newton didn't even understand how an apple fell from the tree. That was over 300 years ago. Newton, from Galileo's thoughts, was able to develop what we know now as modern physics, the laws of mass and motion. The fact that he was able to verbalize, these foundational pieces of the universe at that time was astonishing. I don't think any one of us 300 years ago would understand how that apple would fall from the tree. That is just a complete random aside, but I find it incredible that our ideas of the universe are, you know, based from this man's ideas, and people were like, he didn't understand how apple fell from a tree. Anyways, okay, back onto the topic. Okay, so Einstein's general relativity gave us, this new picture of the universe, one where gravity wasn't this mysterious force pulling at a distance, but the curvature of space-time itself. Now, massive objects like stars and planets bend the fabric of space and other bodies move around it. So think of the sun and the earth, right? But this raises a question. What happens when something is just so big that it bends space beyond repair? So, before the Manhattan Project, Oppenheimer was a theoretical physicist who deeply engaged in general relativity and quantum mechanics. And in 1939, with his student Hartland Snyder, he published a paper on continued gravitational contraction. Just want to make sure I get that correct. So, this paper is often considered the first theoretical description of what they now call a black hole. Right? The term wasn't coined just yet. So, they showed that when a massive star runs out of fuel and can no longer support itself against gravity, it could collapse indefinitely, forming what we now describe as this region of space from which nothing, not even light, can escape. So Oppenheimer and Snyder created the first modern thought experiment of a black hole, well beyond his development of the atomic bomb in the 1940s. And what's really exceptional about that is that, through thought experiments about collapsing stars, purely theoretical from Einstein's ideas and equations, and through Newton's equation or Newton's ideas, we helped shape Oppenheimer's mindset long before he ever worked on the atomic bomb. He was literally studying how mass and energy and how those collapse behave at their limits. And that same understanding of how matter can release immense energy under extreme conditions became the conceptual foundation for nuclear fission. So these conceptual ideas of a black hole led to the creation of a completely different field. And what's just immaculate about that is that science has no boundaries. Scientific imagination crosses these borders of applications and fields to develop these tools. It's incredible. Okay, so that the term black holes hadn't been coined yet. This was in 1939, okay? And Oppenheimer's idea was not well received. And so John Wheeler, who is a Princeton physicist, I believe, this, I could be mistaken, I believe he had a fairly negative view of this idea of collapse. But in 1960, he re-examined Oppenheimer's work as, general relativity gained like a bunch of attention. And in 1967, Wheeler coined the term black hole, which is a very vivid image for a region from which no light can escape. So around this time, the concept of singularity took shape, the center point of infinite density in zero volume where physics itself breaks down. Now, mathematicians Roger Penrose, Stephen Hawking, they used Einstein's equations to prove that singularities are not rare, but they're inevitable. They're an inevitable outcome of collapse under general relativity. Now, this collapse of physics is incredibly jarring. And so I went to another podcast where um, Janna Levin was speaking about this. She's an astrophysicist, and she goes into the depths of the cosmos, black holes, and these perceptions. Okay, so she states a black hole is not a thing, but a place where rules change. In her work, especially Black Hole Blues and other songs from outer space, she describes how black holes challenge the very concepts of reality. They erase information, they twist space-time, and challenge our very concept of reality, right? They confront the limits of our understanding. So she describes them as not cosmic monsters, but existential mirrors, which crazy. Okay, so to describe how space-time is manipulated or how it flips at the event horizon, that entrance into the black hole, um, she describes the floating observers. So imagine we are in the International Space Station and we are close to a black hole, close enough that we can see the event horizon, but not close enough to be sucked in. Now imagine our buddy astronaut jumps out of the International Space Station and heads towards that event horizon and approaches it. To the observer, to us, to the people in the International Space Station, the falling person, the person falling into the event horizon, seems to slow down and then freeze at the event horizon, stopping. They fade into red light and time appears to completely stop. They're frozen at the event horizon. Now, for the falling person, time feels normal. They cross the event horizon without noticing a barrier, and the rest of the universe, time seems to speed up infinitely. Space and time literally flip roles inside this event horizon. Time always moves inward towards the singularity, the same way we can't move backwards. Another way I read it described as, space is where we are, time is when we are. And at the event horizon or inside the event horizon, space becomes inevitable as time is inevitable now for us in our current perspective. And while I can't currently wrap my head around that, I will get back to that and describe it at a certain point. I mean, how do you describe four dimensions and how do you describe them flipping and changing roles? And that perception is the limit of our understanding, right? So, for decades, black holes, these ideas only existed on paper, right? Even Einstein doubted that they could even exist. Yet in 2015, gravitational wave detectors heard two black holes merge. And in 2019, the Event Horizon Telescope gave us the first image of a black hole. And so, what began as Oppenheimer's thought experiment from Einstein's theoretical ideas became a photograph, and confirming that the universe does, in fact, fold in on itself. Black holes mark the edge of what we can know right now. Our laws of physics stop working. So, what happens beyond what we can't see, and does meaning or information just disappear? So, to recap, we have Galileo's journey on this ship, to Newton's redefining, to Einstein's brand new conceptualization of relativity, to Oppenheimer's collapsing stars, shows how these ideas become scientific instruments, right? I saw that, black holes became this bridge between imagination, evidence, and math and meaning. And when I think about black holes, I also think about death, right? Both are these inevitable things. Both mark a boundary beyond what our understanding lies. And we can describe what leads up to them. We can describe the collapsing star. We can even look at the event horizon, right? We can see it. And with us, we see our bodies aging. We see people dying. We see that death, but not truly, we don't see what happens beyond that. We can't follow people in. We can't follow people in death, and we can't follow people into the event horizon. And so, just like black holes challenge our knowledge of physics and our laws of physics, death challenges the limits of meaning. And, it just reminds us that, right now in our current society, in our current universe, we can measure and map and develop all these beautiful pieces of technology, but there are still places and moments that exist beyond our explanation. And maybe it's not something to fear. It's something I fear a little bit, right? Maybe it's what keeps us going, keeps us searching. And while we won't see that great discovery, right? Newton didn't get to see the great discovery. Future generations, 300 years from now, may see that future discovery. Okay, so that is all I have for today's Curiosity Council, and I'm sure I'll be back with more black hole topics at some point. So thank you for listening.